Energy transfers and takes on many different forms. Some of these forms are calculatable, so we can have a quantifiable or measurable amount of energy. Energy is the ability to do work, or in this case, to move something, to apply a force. We have a graph that represents the force pulling on a spring versus the distance it is stretched. This is storing energy as elastic energy because we're stretching or compressing something. If we use y equals mx plus b, we can represent it graphically. There's our slope. We just give it a general letter k. In this case, though, the k represents a very important value, the spring constant. The spring constant tells you how stretchy or not so stretchy a spring is. The higher the spring constant, the tighter the spring. The lower the spring constant, the looser the spring. The unit for the spring constant is newtons over meters because its force is its rise and then its run is distance or displacement. In order to calculate the force that it takes for a spring to be compressed or stretched, we can use this formula. Force in newtons is equal to our spring constant, which is in newtons over meters, times displacement, or how far the spring was stretched. You're going to use this formula when you're either given a force or when you're solving for a force. Let's go back to the graph of the force needed to stretch a spring versus the distance it was stretched. We found that the slope represents k, or our spring constant, how stretchy or not so stretchy a spring is. The area underneath, though, is also important. It's energy. If I wanted to calculate from this graph the amount of energy, I would take the area underneath the graph. In this case, I'm using 1/2 base times height, so if instead my base is x, my height is f, I can rewrite this formula. If I need to find the amount of energy required to compress a spring or to stretch a spring, I would use this formula based on the area underneath the formula and the force formula that we just calculated. I use this whenever I know just the spring constant, just the distance, or just the energy, or I'm finding any of those. If force is involved, I do not use this formula. This is how I calculate my elastic energy in joules. This tells me how much energy is stored or how much energy it took to compress the spring. K is my spring constant, how stretchy or not so stretchy a spring is. And then x is my displacement. Remember, it's the displacement of how far the spring was stretched. If the spring started as 1 inch and I stretched it to 3 inches, x equals 2 inches. Let's try a couple of example problems. I'm going to start with a spring on a pinball machine. It has a spring constant, K, of 2.5 Newton meters. It's compressed 0.05 meters. I want to find out how much force. If force is involved, I use my force formula. Spring constant times distance of stretch. I'm solving for F, so it's going to remain a variable. Everything else gets plugged in. 2.5 for K, 0.05 for the distance it was stretched, and I just plug and chug. It took about 0.125 newtons to compress that string. The spring on the pinball machine with a spring constant of 2.5 Newton meters is compressed 0.05 meters. How much energy is stored? Force is not involved, so I'm going to use a different formula. Plug in what I know. I'm trying to find energy, so energy remains a variable. The 1/2, that's just a constant value. The square, that's an operation, so it comes right down. K is my spring constant, newtons over meters. It was stretched 0.05 meters, or compressed 0.05 meters. Now it's just a matter of doing the order of operations. I squared my 0.05, then I'm going to multiply together. 1/2 of 2.5 times 0.025 gives me a very small amount of energy. 0.003, you can round it to 0.003 joules. Remember, joules is the unit for energy. It's how much energy is stored in this spring. The gravitational energy equation is very familiar. It's the amount of energy that an object can potentially turn into another form of energy. We know that gravitational energy has everything to do with two variables, mass and how high off the ground it is. Something that's held higher up can use more energy. So that's why something falling from a higher location moves a lot faster. Here's our formula. Eg is the amount of gravitational energy in joules, 9.8 our gravitational force constant here on Earth, and then mass, which is in kilograms always, times the displacement. Now this is the height off the ground. Displacement for elastic energy has to do with how far the spring was stretched. Displacement for gravitational energy has to do with how high off the ground the object is. Something that's pulled higher up has more energy stored in it, just like something that has more mass held off the ground has more energy in it. Gravitational energy is when an object's off the ground. As it falls towards the ground, it starts to move, turning into kinetic energy, which we can also calculate. Kinetic energy is the energy needed to keep an object moving. The faster the object, the more kinetic energy, just like the higher up an object, the more gravitational energy. Here's our formula. E sub k, that's the kinetic energy. That's how much energy we have stored. 1/2 is just 1/2. M is mass, always in kilograms. And then v is our velocity. It's how fast the object's moving, v squared. Let's try a problem or two. A 3-kilogram apple, so we know its mass, is held 4 meters above the ground, so we know how high above the ground it is. How much energy does it have stored in it? We need to look at what form of energy is acting on this apple. It's not moving, so no kinetic. It's not stretched or compressed, no elastic, but it's off the ground, so I need to use my gravitational formula. I'm solving for energy, so I leave energy by itself. 9.8 comes down. The mass is 3. The displacement is 4, because it's 4 meters above the ground. Now it's just order of operations. 9.8 times 3, 29.4 times 4, and that's how much energy is stored. If the apple was higher off the ground, it would have more gravitational energy. If the apple was lower to the ground or closer to the ground, it would have less gravitational energy. Now we have a jogger that's moving 5 meters per second, so we know their velocity, and has a mass of 105 kilograms. How much kinetic energy does the jogger have? I know that we're on the ground, so there's no gravitational energy. The jogger has not been stretched or compressed, so there's no elastic energy. However, they're moving, so there's kinetic energy. Use the right formula based on the type of energy being used at that moment. I'm going to plug in what I know. I need to find energy, so I'm going to leave energy as a variable. I'm going to plug in my mass of 105, my velocity of 5, and now it's just order of operations. I'm going to square my 5. Half of 105 times 25 gives me 1,312.5 joules. If the jogger was running faster, they would require more energy. If the jogger was running slower, they would require less energy.